So now we're talking about the continuation, or the follow-up to the F formula, which basically teaches you how to prove the three groups are the same, or is there a difference among any of the three groups. And this is how you write out the hypotheses. We use the numbers. I remember 787. What were the numbers last time for?
First column was 342.
342. Okay, so just make this into a 3. Okay, so, and then of course, just to remind you how this is done, we plug this into a Anova Table, which helps you organize your calculations. It's called the Anova Table, which consists of about 4 or 5 columns. It's called the source of variation, what was next? The degree of freedom, or the MS we had next? MS, the DF. I'm sorry, this is the next. The first thing was the SS. So a lot of books get to put the DF first, but then comes the MS, and finally there was another column called the F, and there were rows to the table called the MSA, or this was the among. This was the within. This was the total. This was the SSA, the SSW, the SS total we never bothered calculating. This was C minus 1. This was N minus C. This is N minus 1. This was equal to something called the MSA, which was this divided by that, MSW, which was this divided by the second column divided by its degree of freedom. And finally, the F is equal to the MSA divided by the MSW. And then we went to the F diagram, which began with a 0, had a bump at the beginning, only had a one-tail rejection region, so there's no problem about chopping the alpha in half. You never do that. This was do not reject a 0. And finally, we took the F number that came out of this thing here. This was the F equals this, and we made an arrow, and we decided based on the degree of freedom of the numerator, the degree of freedom of the denominator. There were 2 different degrees of freedom, if you recall. And finally, make your decision. So now the question is, after you make your decision, let's say you decided to reject a 0. Well, let's go back. Well, let's say you decide to accept a 0. Then you stop right there. You've proved all the drugs are the same. There's nothing to say any further about it. But very often you end up rejecting a 0, which means the drugs are not the same. Can somebody please tell me? I know I told you I was going to call on people, but I've been for 35 years, I haven't been doing that, so it's hard to change that. Can somebody please tell me what would be a good follow-up question as you as a business person or somebody using this data would want to answer? We just decided, yes, Anon. What? Well, that's a good answer. How different is it? That's certainly reasonable, but that answer is really based on the F. The bigger the F, the more different they are. So we sort of answered that already, but you might want to fine-tune that. So that's not a bad answer. Yes? Yeah, which is different. Maybe, for example, these two are the same, and this one's different than both of them. This is much higher than both of them. Well, maybe this one is really high or really low, and the other ones are about the same. So we don't know. We want to know which drug is causing the difference, and that really requires 3 separate answers. Is the first different than the second? Is the first different than the third? Is the second different than the third? So 3 separate little answers will be the answer to the following question. And the method to do, there are many, many methods to do it, and they're all called post-hoc tests because it's after the fact. In other words, if you can't do this until after you rejected a 0. You can't just start it. You can't start off by using this method. You got to first use this method, and that's the first thing. And it's called multiple comparison because we're going to have many pairs of pairwise because we're comparing a pair at a time, multiple comparison because we're dealing with many comparisons, and there are many formulas, pairwise multiple comparison post hoc tests. The one we're going to be showing you, because the book has it, is called the Tukey-Kramer. And they're pretty, I think Tukey just died. Kramer, I don't know what happened to him, but these are pretty recent formulas. Tukey-Kramer pairwise multiple comparison post hoc test. Now, and it's going to basically be, you're going to take the first average compared to the second average, and you'll decide are they close together or not. Then you're going to, if it turns out you say either yes or no, then you're going to compare the first average to the third average, and you'll say yes or no, they're the same or different, etc. So you're just going to repeat this formula 3 times. But there's a question that somebody should be asking me right now. If you're following this basic theory of the chapter, especially what we said at the very beginning of chapter 11, you might ask me a good question. Yes, Calvin?
If we, instead of rejecting H0, accepted H1, we shouldn't be doing this. Because
You mean, no, you get the very first, I know you're asking a good question, but if we don't reject a 0, and in addition we accept a 0, not reject, okay, then we shouldn't be, the answer is yes, you don't do it. If on a test I say, part 1 for 50 points, calculate the F. Part 2 for 30 points, calculate the Tukey-Kramer, but let's say you accepted the A0 for the F. What should you do? Well, the first, you should raise your hand. You should say, Professor, what do we do? I would tell you do the Tukey-Kramer anyway, because I want to see if you know how to do the calculations. But in real life, you wouldn't do it. So for the test and for the spinner project, do it, but in real life, you wouldn't do it. Okay. So but I'm asking you for a more basic question that somebody might think of, and the answer, I'll provide the answer myself, because I don't want to spend the whole day here on that, which is, we just started off the chapter by saying we can't do chapter 10 of comparing group 1 to group 2, then group 1 to group 3, then group 2 to group 3. We said that was illegal because it messes up the alpha. The question, why is it okay to do it now? I'm telling you, we're going to compare 1 to 2 and 1 to 3. Why is it okay now when it wasn't okay at the beginning of the chapter? What do you see? I hope you understand the question, and anybody have an answer? Yes, Anna. I'm sorry, say again? No. Last time we did no. Now the problem that we raised at the beginning of the chapter is that you can't compare 2 at a time, because let's say you have 7 drugs. There are so many compared: the first to the third to the fifth, the fourth to the seventh. That somewhere along the line you're bound to make a type 1 error. So we couldn't do that. So why is it okay to do it now? Yes. Because, well, the answer is we already did the proper method of comparing all of them simultaneously by the F, and we already know there's a difference among the drugs. Now, we're not discovering it when it's not appropriate, when it's not really real. We know for a fact there is a difference among the drug. All now we're doing is trying to find that difference. So it's a little different than before. Secondly, the Tukey-Kramer test, which I'm going to show you, has built into it, it adjusts the alpha in a simple way so that you don't mess up the alpha by doing it so many times. So it turns out that is a problem, but we are dealing with it now. So now what's the Tukey-Kramer test? The Tukey-Kramer test suggests making the following chart. And I don't know if, am I on the screen? Well, that solves the problem. Okay, this is now the Tukey-Kramer. It basically tells you to solve the problem in 4 steps, and there are 4 simple steps. Okay, the first step is going to be called the hypotheses. What's the hypotheses? I guess ES. This is going to be the calculation, because this is true for every hypothesis. Next is going to be called not the diagram, but basically the diagram helps us figure out the boundary. And we call that the critical range. The critical range is basically a fancy name for the boundary, which usually we get out of a picture, but for some reason in this particular section I'm not going to show you. The only exception where I'm not going to show you a picture, called CR. And finally, you can make your conclusion. So the basic structure of this particular problem is the same as all the other problems, except instead of doing it 1 time, we have to do it, in this case, 3 times. We have to figure out if the first mini H0 mu1 equals mu2, or the possibility is that mu1 is not equal to mu2. Then we can figure out H0 mu1 is equal to mu3 possibly, or those 2 drugs are not different, or maybe mu1 is not equal to mu3. But we have to repeat this in this case a 3rd time. If some of the homeworks where they give you 4 columns of numbers, and you have to compare the first to the second, the first to the third, the second to the fourth, how many comparisons are going to be if there are 4 columns of numbers? No. How many comparisons you're going to have when there are 4 columns of numbers to start with? Anybody? Yes. Nope. Close, but not right. 4 columns of numbers. Now you can do it by doing in your hand 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. 6 of them. Or you can do it by the formula 4 choose 2 from stat 1, 4 factorial over 4 minus 2 factorial over 2 factorial, which also comes out to 6. So with 4 columns, there are going to be 6 comparisons. You're going to have to do the same thing 6 times. When there are 2 columns, how many times you got to do it? Just one? No, not even one. How many? If there are 2 columns, how many times you got?